Right now, somewhere in this galaxy, a star is taking its last breath, and everything we thought we knew about how stars die was wrong. I want you to stay with that sentence for a second, because I'm not using it as a dramatic opener to hook you and then deliver something disappointing. I mean it exactly as I said it. The version of stellar death you learned in school, red giant, white dwarf, done, is like being told a film ends with the protagonist dying without ever being shown the story. This video is the story. By the end of our time together here, you'll know exactly what our sun's final hours will look like, event by event, and you'll understand why the real process is far more violent, far more beautiful, and far stranger than any classroom ever conveyed. Now, I should tell you up front, when I say, the last 24 hours, I'm using that loosely. For some stars, the finale takes minutes. For others, thousands of years. But stay with me, because we're going to compress this into the most dramatic timeline you've ever heard, and the 24 hours label is going to make complete sense by the time we get there. We're not starting at a star's birth. We're starting at the moment of no return, when silicon burning begins in the core of a dying massive star. The star doesn't know it's dying yet. But we do. Let's start with what a star actually is, because I think most of us have been carrying a fundamentally wrong picture of this our entire lives. When you look at the sun, you see a stable, warm, constant presence. Something reliable. Something that rises every morning and will rise again tomorrow. And in human terms, that's completely accurate. But zoom into the physics, and what you're actually looking at is a controlled detonation that has been running for 4.6 billion years without stopping. Every single second, 600 million tons of hydrogen are fused into helium in the sun's core. The only thing, preventing instant gravitational collapse is the outward pressure generated by that fusion. If you could somehow stop the fusion process right now, the sun would implode in roughly 30 minutes. It is, at every moment, simultaneously almost exploding and almost collapsing. I remember the first time someone explained this to me properly. I had to sit with it for a while. Because it changes how you look at a sunrise. That light isn't just warmth, it's the evidence of a suspended crisis that's been successfully maintained since before our planet existed. Here's the reframe that matters: a star isn't burning. It's falling, and the explosion of fusion is the only thing stopping it from hitting the ground. Gravity is always winning, slowly, grain by grain. Fusion is always losing, buying time, second by second. The sun converts roughly 4 million tons of its own mass into pure energy every single second. This is Einstein's E equals mc squared in action at a scale that makes the equation feel almost abstract. It has been self-consuming since before Earth existed. And the core temperature, currently around 15 million degrees Celsius, compared to a surface of just 5,500 degrees, has been slowly rising over billions of years. That rising core temperature isn't a sign of health. It's a slow trigger. What determines how a star dies is decided at its birth, entirely by mass. A star's mass is its destiny. Stars below about 8 times the mass of our sun, including the sun itself, will die quietly, beautifully, without explosion. Stars above 8 solar masses will die in the most energetic events the universe produces. We're going to follow both paths today. But there's one detail I want to plant in your mind before we go further, because it's going to come back and reshape everything when we reach the climax of this story. There is one element, a single element on the periodic table, that no star in the universe can fuse for energy. When a massive star starts producing this element in its core, a countdown begins. The star cannot stop it. The laws of physics do not permit escape. That element is iron. And the reason it's a death sentence for a star is something we'll get to very soon. Now let's go inside a massive star, something 8 to 20 times the mass of our Sun, and watch what happens in its final stages. Because the timeline of what occurs here is one of the most genuinely stunning facts in all of astrophysics. Massive stars fuse elements in a layered structure. Astrophysicists call it the onion model. At the center, the most recently fused, heaviest element. In concentric shells outward, progressively lighter elements still fusing around it. Hydrogen burning at the outermost shell. And in sequence, working inward, helium, carbon, neon, oxygen, and finally silicon burning at the core. What makes this staggering is how the timescales compress. Hydrogen burning, roughly 10 million years. Helium burning, about 1 million years. Carbon burning, around 1,000 years. Neon burning, approximately 1 year. Oxygen burning, 6 months. And then silicon burning, the final fusion stage before iron dominates the core. Silicon burning lasts about 1 day. That is where the title of this video comes from. That is the literal last 24 hours of a massive star's fusion history. We've gone from million-year timescales to something you could theoretically miss if you weren't paying attention on a Tuesday. The star has been fusing elements for tens of millions of years. Its finale is a single day. During those final 24 hours, the exterior of the star looks completely normal. If you were a civilization orbiting this star, if you had built cities, written histories, looked up at your Sun for thousands of generations, you would have no warning. The sky looks identical. The star hasn't changed color. You cannot see what's happening inside. Death by internal betrayal, completely invisible from outside. I want to be honest about something here. When astrophysicists say, about a day, for silicon burning, that's not a precise alarm clock. It could be 12 hours. It could be 36. The timescale depends on the star's mass and composition in ways that make exact prediction impossible. The point is that we've gone from geological timescales to something measured in hours. That's the number that should stop you. The iron core grows with every passing hour of silicon burning. Every second, more iron accumulates at the center. But here's the problem: iron fusion requires more energy than it releases. Fusing iron is thermodynamically impossible for profit. The star is filling its own core with thermodynamic dead weight, and there is no fusion process available to resist what comes next. The core is building toward a threshold, the Chandrasekhar limit, roughly 1.4 solar masses, beyond which electron degeneracy pressure, the last quantum mechanical defense the star possesses, will fail completely. The last element a massive star ever fuses doesn't release energy when it fuses. It absorbs it. Which means the moment iron production begins, the star is already writing its own death warrant, 1 hour at a time. The iron core reaches the Chandrasekhar limit. And what happens next happens so fast that human language almost fails to describe it accurately. The core freefalls inward at roughly 25% of the speed of light. Not gradually. Not in stages. Instantly. In 0.1 seconds, 1/10 of 1 second, the core collapses from a sphere roughly the size of Earth, about 12,000 kilometers across, down to approximately 20 kilometers in diameter. This is the birth of a neutron star. Let's make the density real for a moment. The material in that 20-kilometer sphere is compressed to 10 to the power of 14 grams per cubic centimeter. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth's surface. This isn't a metaphor or an approximation, This is the measured physics of neutron degeneracy, the quantum mechanical state where protons and electrons are forced to merge into neutrons, and the Pauli exclusion principle, the rule that no two identical fermions can occupy the same quantum state, becomes the only remaining defense against further collapse. The energy released in that 0.1 seconds is approximately 3 times 10 to the power of 46 joules. To frame that, our Sun will emit energy across its entire 10 billion-year lifetime, and the core collapse of a massive star releases roughly 100 times more than that, in a tenth of a second. But here's something that will genuinely recalibrate your sense of scale. 99% of that energy doesn't go into the visible explosion. It escapes as neutrinos, subatomic particles so weakly interacting with normal matter that they pass through the entire Earth as if it weren't there. 65 billion solar neutrinos pass through your thumbnail every second right now, and you feel absolutely nothing. Yet in a core collapse, the neutrino flux becomes so extreme that even their near-zero interaction probability becomes physically significant. The neutrinos literally help drive the explosion. The most antisocial particles in the universe end up being responsible for blowing a star apart. The neutron star's formation sends an outward shockwave tearing through the infalling stellar material at 30,000 kilometers per second, 10% of the speed of light. But here's the problem: the shockwave stalls. It runs headlong into the massive outer layers still falling inward, and it loses energy to the extent that for somewhere between 100 and 500 milliseconds, the supernova almost fails to explode. The star hangs in the balance. For half a second, physics is undecided. In 1987, a supernova in the Large Magellanic Cloud, SN 1987A, 168,000 light-years away, gave us something extraordinary. 12 seconds before any light from the explosion reached Earth, neutrino detectors in Japan and the United States registered the burst from the core collapse. 12 seconds before the sky confirmed what had happened, the instruments already knew. We detected the interior event before we could see the explosion. Scientists sitting at their detectors watched a number appear on a screen that meant, a star just died, on the other side of the universe, 12 seconds ago. I genuinely get chills every time I think about that. It confirmed the entire theoretical model of core collapse in real time. And what saved the stalled shockwave in SN 1987A, what saves it in every successful core collapse supernova, is those same neutrinos. Depositing just enough energy in just the right region to revive the shock and push it over the edge. The universe saves its own explosion with particles that refuse to interact with almost anything. The revived shockwave tears outward through the star's remaining layers. It takes several hours after the core collapse for the explosion to reach the surface, during which time the interior is obliterated, but the exterior still looks normal. There is a delay between the death and the announcement. When the shockwave finally breaks through the surface, an event called shock breakout, there's a brief, ferociously intense flash of X-rays and ultraviolet radiation lasting only minutes to hours. This is the first visible sign that the star has died. We have caught this precise moment in direct observation only twice. The first confirmed detection came in 2016 from a star catalogued as KSN 2011b, observed by the Kepler Space Telescope almost by accident while it was scanning for exoplanets. A star died. Kepler happened to be watching. And for the first time in history, humans saw the exact moment a supernova announced itself. At peak brightness, a Type II supernova reaches luminosities that beggar comprehension. For several weeks, a single exploding star can outshine its entire host galaxy, every one of the hundreds of billions of stars that galaxy contains. The death of one star overwhelms the combined light of everything else. And then comes the revelation that reshapes everything when you truly sit with it. The supernova explosion is how every heavy element above iron was made. Gold, silver, iodine in your thyroid gland, the calcium in your bones, the iron in your blood, none of it existed before a stellar explosion created it. These elements were forged in the core of a dying star and scattered by the explosion into the interstellar medium. The outer layers of the exploded star travel outward at 10,000 to 30,000 kilometers per second, seeding the surrounding space with the building blocks for new stars and new planets. The death doesn't just produce wreckage. It produces raw material. The Crab Nebula, what we see when we look at the remnant of a supernova recorded by Chinese astronomers in 1054 CE, visible in daylight for 23 days, is that explosion still expanding, nearly 1,000 years later, still scattering the elements of a dead star across the cosmos. You are not watching a star die. You are watching your own origin story. I've read that fact probably 100 times while preparing this video. I still haven't fully processed it. Some things are meant to be larger than what a single thought can contain, and I think this is one of them. The remnant left behind after a Type II supernova is either a neutron star, a 20-kilometer sphere of pure nuclear matter rotating hundreds of times per second, radiating beams of electromagnetic energy as a pulsar, or, for the most massive progenitors, something else entirely. Something from which no information, no light, nothing at all can ever return. But let's set that aside for a few minutes, because there's an entirely different way a star can die, and understanding it matters personally, because it's the fate of every star within about 50 light-years of Earth. Stars below about 8 solar masses, the vast majority of stars in the galaxy, including our Sun, never develop the iron cores needed for core collapse. They never go supernova. Their story ends differently. Not with a detonation, but with something that, in some ways, I find more haunting. In approximately 5 billion years, the Sun exhausts the hydrogen fuel in its core. Fusion there stops. The core contracts under gravity, heating further. The outer layers, responding to the changed pressure balance, begin to expand. The Sun swells into a red giant, growing over the following billion years to somewhere around 200 times its current radius, potentially engulfing Mercury, certainly engulfing Venus, and placing Earth's fate in genuine uncertainty depending on how much mass the Sun loses during the expansion. But here's the timeline detail that matters more than the red giant itself. Long before the Sun physically expands to swallow anything, the gradual increase in its luminosity will have already ended complex life on Earth. In roughly 1 to 2 billion years, not 5 billion, the Sun's output will have increased enough to begin boiling Earth's oceans. The red giant phase is not what ends us. The slow brightening, already underway, is the actual clock. During the red giant phase, the Sun sheds mass through a dramatically enhanced stellar wind. It will lose roughly 45% of its total mass this way, and as it loses mass, the planet's orbits gradually widen, which is part of why Earth's fate during the eventual red giant expansion is genuinely uncertain. The math is complicated by the fact that you're trying to calculate the orbit of a planet around a star that is simultaneously expanding and losing mass in a way that's difficult to model precisely. At a core temperature of around 100 million degrees Celsius, helium fusion ignites in what's called a helium flash. This is a brief, violent event releasing as much energy as the entire current Sun manages in a matter of seconds, but it's completely trapped inside the star and produces no visible change from outside. The star keeps its secret again. Later, in what astrophysicists call the asymptotic giant branch phase, the Sun undergoes thermal pulses, oscillations of helium shell burning occurring roughly every 100,000 years. Each pulse expels material into the surrounding space. And eventually, after enough of these pulses, the outer envelope of the Sun detaches entirely and drifts outward into space, a planetary nebula. The name is a historical accident. Early telescopes made these expanding shells look vaguely like planetary disks. They have nothing to do with planets. What they actually are is a star's final exhale, and they are among the most beautiful objects the universe contains. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, 650 light-years away and 2.5 light-years across, which would extend past our nearest stellar neighbor if placed where our Sun is. Someone once called the Helix Nebula the Eye of God. What it actually is, what every planetary nebula actually is an obituary. The most gorgeous obituary the universe has ever written. And something I find genuinely moving about them is that the star had to die for them to exist. The beauty requires the death. They're also temporary. By cosmic standards, the glowing shell disperses into interstellar space in roughly 10,000 to 20,000 years. The most beautiful moment is also the briefest. When the planetary nebula shell drifts away, what's left behind is the exposed stellar core, a white dwarf. And understanding what a white dwarf actually is changes how you think about the end of the universe itself. A white dwarf is not burning. It has no fusion happening. It is the compressed remnant of a stellar core, composed primarily of carbon and oxygen, held up by electron degeneracy pressure, the same quantum mechanical rule we encountered in the neutron star, but operating at lower densities. It has no energy source. It is simply radiating the heat stored from its previous life, slowly, across timescales that make the current age of the universe seem brief. The cooling timescale for a white dwarf is extraordinary. The universe is 13.8 billion years old. The coolest white dwarfs we have detected are roughly 11 to 12 billion years old, and they are still significantly above absolute zero. We have never found a black dwarf, a white dwarf that has cooled to thermal equilibrium with the cosmos, because the universe is not old enough to have made one. Every white dwarf that has ever formed is still glowing somewhere in the universe right now. Every quiet stellar death we know of is still leaving a light on. Sirius B, the white dwarf companion of Sirius, the brightest star in our night sky, is about the size of Earth but contains roughly the mass of our Sun. It has been cooling for approximately 100 million years. It is still 25,000 degrees Celsius on its surface. And then there's BPM 37093, 50 light-years away. This white dwarf has a crystallized core. The carbon, under those pressures, has literally settled into a crystalline structure. Astrophysicists calculated the crystal mass at approximately 10 to the power of 34 carats. The star is a diamond. Not poetically, physically, structurally, a diamond floating in space. After all that violence, all those billions of years of fusion and thermal pulses and ejected shells, the remnant of some stars is a gem. I've been sitting with that one for a while and I'm still not sure what to do with it. But white dwarfs have one more story they can tell, one that demonstrates that even in death, stars can surprise you. In binary star systems where a white dwarf has a companion, the white dwarf can accrete material from that companion. If it accumulates enough mass to once again approach the Chandrasekhar limit of 1.4 solar masses, it undergoes thermonuclear explosion, a type Ia supernova. Unlike the core collapse events we discussed earlier, this explosion is complete. There's no neutron star left behind, no remnant. The white dwarf is entirely vaporized. These type Ia explosions are so consistent in their peak brightness that astronomers use them as distance markers, standard candles, to measure how far away their host galaxies are. The discovery of dark energy in 1998, the realization that the universe's expansion is accelerating rather than slowing, was made possible by measuring type Ia supernovae at enormous distances and finding that they were dimmer than expected. The death of stars, recycled into a tool for measuring the geometry of the cosmos. Subramanian Chandrasekhar calculated the mass limit that bears his name during a ship voyage from India to England in 1930, when he was 19 years old. His senior colleagues initially dismissed the result as mathematically interesting but physically irrelevant. He received the Nobel Prize 53 years later, in 1983. For the most massive stars, those above roughly 20 to 25 solar masses, neutron degeneracy pressure is not the final answer. After core collapse, the neutron star that briefly forms continues to collapse inward past its own Schwarzschild radius. In less than a second after the core bounce, it becomes a black hole. The Schwarzschild radius of a stellar mass black hole of about 3 solar masses is approximately 9 kilometers. The neutron star, already compressed to 20 kilometers across, collapses through this threshold so rapidly that it happens faster than the surrounding material can react. Let me be precise about what a black hole is and is not, because the word hole is genuinely misleading. It isn't empty space. It isn't a void. It's a region where space-time curvature is so extreme that the escape velocity exceeds the speed of light, meaning that once you cross the event horizon, not even light can travel fast enough to escape the gravitational gradient pulling it inward. Inside the event horizon, the singularity isn't a location in space. It is a location in your future. You cannot avoid it any more than you can avoid tomorrow. The laws of physics as we understand them don't offer an alternative. In 2009, astronomers monitoring a red supergiant in galaxy NGC 6946, sometimes called the fireworks galaxy for its prolific supernova rate, observed something deeply unsettling. A star designated N6946, BH1 briefly brightened, then simply vanished. No supernova. No explosion. No dramatic announcement. A star hundreds of times the mass of our Sun, which had been burning since before our solar system formed, was there one observation and gone the next. The leading explanation is direct black hole formation. The collapsing core crossed the event horizon and the remaining stellar material followed, silently. A star that had existed for millions of years simply ceased to be visible one day, and the universe did not announce it. If our Sun did that tomorrow, not that it can, the Sun is not in this mass category, and I want to be clear, I'm not trying to alarm anyone, but hypothetically, if a star within our visible sky simply vanished in this way, we'd have no warning. The light takes time to travel. We would only notice the absence when we looked. Tidal forces near a stellar mass black hole, below the event horizon specifically, create a gradient differential between the near side and far side of any infalling object that exceeds the structural strength of matter. Protons, neutrons, electrons, all stretched into a narrow stream of particles following geodesic paths toward the singularity. Astrophysicists call this process spaghettification. That is the actual technical term used in the peer-reviewed literature. Somehow this remains one of my favorite facts about physics, that at the extreme terminus of physical reality, the most precise scientific word available is one that sounds like something from a children's menu. Black holes also die, eventually. Quantum effects near the event horizon cause pairs of virtual particles to form, with one falling in and one escaping as radiation. This Hawking radiation causes the black hole to very slowly lose mass over time. A stellar mass black hole would take approximately 10 to the power of 67 years to fully evaporate. To give that number context, the current age of the universe is 13.8 times 10 to the power of 9 years. Even black holes, the most absolute structures physics permits, are not permanent. They just require a patience that makes geological time feel impulsive. And while we're in this territory, a brief note on neutron star mergers. When two neutron stars spiral into each other over billions of years and finally collide, the merger produces gravitational waves, a kilonova explosion, a black hole, and heavy elements. gold, platinum, uranium. The R process, rapid neutron capture, that creates elements heavier than those a supernova can make, happens in the fraction of a second during a kilonova. A single merger can produce a mass of gold equal to several times Earth's total mass. The LIGO Observatory's detection of GW 170817 in 2017 was the first direct observation of such an event, accompanied by light across the entire electromagnetic spectrum, and confirmed that the gold in your jewelry came from the collision of two dead stars. There is a star 700 light-years from Earth that astrophysicists have been watching with increasing attention for several decades. In late 2019, it did something unexpected. Betelgeuse, the red supergiant marking Orion's right shoulder, dimmed to approximately 35% of its usual brightness between October 2019 and February 2020. Astronomers called it the Great Dimming. On social media, in news headlines, in millions of conversations among people who hadn't looked at the night sky in years, the question spread, was Betelgeuse about to go supernova? I'll be honest, during those months, I checked astronomy news more often than I care to admit. There was something electric about the possibility. Not hope that it would explode, exactly. More an awareness that if it did, and if you happened to be outside on the right night, you would witness with your own eyes something no human in recorded history has witnessed from this distance. The resolution was simultaneously anticlimactic and scientifically fascinating. After comprehensive observation, the consensus emerged that a massive convective plume had ejected superheated gas from the star's surface. That gas cooled rapidly in space, condensed into dust, and the dust cloud obscured part of the star from our line of sight. Betelgeuse sneezed. The dimming was a localized atmospheric event, not a precursor to explosion. But the Great Dimming triggered the most detailed study of Betelgeuse's interior structure ever attempted. What emerged was genuinely informative. Previous estimates of the star's size and distance were revised. Betelgeuse is smaller and closer than earlier models suggested, approximately 750 solar radii in diameter, and roughly 500 light-years away rather than the 700 previously cited. These revisions change explosion timeline estimates, though not by enough to provide certainty in either direction. The honest answer to when Betelgeuse will explode is, sometime within the next 100,000 years. That is the current best estimate. Not within years, not within centuries with any confidence, but within a geological eye blink relative to the star's life. A 2023 analysis suggested Betelgeuse may be in a more advanced evolutionary stage than previously modeled, potentially closer to the oxygen or silicon burning phase we discussed, but the uncertainty in stellar modeling remains substantial. What a Betelgeuse supernova would look like from Earth is worth describing, because it clarifies something about scale. At roughly 500 light-years, the explosion would appear approximately as bright as the full moon, visible in broad daylight for several weeks, casting shadows at night, visible to the naked eye as a distinct star-like object for over a year during the fading phase. It would not be dangerous to Earth. The threshold distance for a supernova to pose genuine biological risk through radiation is estimated at somewhere between 50 and 100 light-years, with considerable debate in the literature about the specifics. At 500 light-years, we would be observers, not victims. James Webb Space Telescope observations of another candidate star, WR-124, a Wolf-Rayet star 15,000 light-years away, released in 2023, revealed the ejected shell surrounding this massive, unstable star in extraordinary detail. A Wolf-Rayet star in this phase is considered a potential direct progenitor of a core-collapse supernova or black hole formation. Webb's ability to image the dust and gas structure around these stars represents a genuine advance in our ability to understand the final stages before explosion, even if predicting the timing remains out of reach. Every atom of carbon in every pencil, every atom of oxygen in every breath, every iron atom in every blood cell on this planet, these atoms existed inside a star that died before our solar system formed. The sun didn't create them. It inherited them, along with everything else that coalesced from an enriched molecular cloud 4.6 billion years ago. We are the legacy of a stellar death that happened before Earth existed. That observation, taken seriously, changes the framing of this entire subject. Carl Sagan's phrase, "We are made of star stuff," has been repeated so often it risks becoming wallpaper. But it is precise nuclear astrophysics. The specific abundances of elements in the human body match the expected output of stellar nucleosynthesis from various types of stellar deaths. Carbon from asymptotic giant branch stars. Oxygen from both supernovae and stellar winds. Iron from type Ia supernovae. Gold and iodine from neutron star mergers. Your thyroid gland contains iodine that was forged in a neutron star collision. That's not a figure of speech. The cosmic recycling mechanism has been running for roughly 13 billion years. Stellar death enriches the interstellar medium with heavy elements. That enriched gas collapses under gravity into new stars, surrounded by planet-forming disks made of the recycled material. Planets form. On at least one such planet, chemistry became biology. And here we are, capable of working this history backward and reading it in the nuclear record of the matter around us. Each generation of stars is richer in heavy elements than the last, because each generation inherits the output of its predecessors' deaths. Our Sun is what astronomers call a population 1 star, third generation, metal-rich by astronomical standards, capable of forming rocky planets with complex geochemistry. The very first stars, population 3, formed from nearly pure hydrogen and helium in a universe that had not yet been enriched by any stellar deaths. Those stars could not have formed rocky planets. They could not have produced the chemical complexity that biology requires. They had to die, in enormous explosions, because they were likely very massive, before the universe was capable of building anything like us. Life as we know it required multiple generations of stars to die first. We are not just made of star stuff. We are made of the specific output of specific types of stellar deaths, accumulated across multiple generations, over billions of years. The delay was necessary. We couldn't have arrived any sooner. The Milky Way has been enriched by roughly 1 billion supernova explosions over its history. Each one scattered heavy elements across light years of space. Our solar system formed at roughly the right moment in galactic chemical evolution, enough heavy elements for rocky planets and biochemistry, but not so late that the galaxy star formation had already significantly declined. And the broader picture is worth sitting with. We live in what cosmologists call the stelliferous era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited. It will end in approximately 100 trillion years, when all available hydrogen in the galaxy has been consumed or locked away in low-mass stars too dim to illuminate anything. After that, no new stars. What remains will be white dwarfs cooling toward absolute zero, neutron stars, and slowly evaporating black holes. The era we inhabit, with its galaxies and nebulae and supernovae and the warmth of a sun on a morning, is a temporary feature of a universe whose future is almost entirely dark and cold. We live in a cosmically privileged moment. Most of the universe's future contains no stars at all. Which brings us, finally, to the most personal question this video can ask. In approximately 5 billion years, everything we've discussed happens here, to our star, our planet, everything humanity has ever built, remembered, or loved. So let's end where we have to end, with our sun's actual last hours. In about 1 billion years, the sun's luminosity will have increased roughly 10% from today. Earth's oceans will begin a slow process of evaporation. Complex life becomes increasingly difficult to sustain. This is not the dramatic finale, it's the beginning of the long goodbye. In 5 billion years, the hydrogen in the Sun's core runs out entirely. The core contracts. Outer layers expand. The red giant phase begins. At 5.4 billion years from now, the Sun enters the red giant phase proper, expanding to perhaps 200 times its current radius. Mercury and Venus are engulfed. Earth's fate, whether it's engulfed or pushed outward as the Sun loses mass, remains genuinely uncertain in the models. The uncertainty isn't a failure of science, it's an honest acknowledgement that predicting the orbital evolution of a planet around a rapidly changing star involves cascading variables that resist precise calculation. The last 24 hours for a Sun-like star don't look like the silicon-burning countdown of a massive star. They are quieter. The final stage before the planetary nebula forms is the last thermal pulse of the asymptotic giant branch, the last spasm of helium shell burning before the outer envelope detaches. In those final hours, the luminosity spikes. Material is expelled at several kilometers per second. The outer layers begin their long drift outward into space. And then, where the Sun was, there is a small, intensely hot exposed core, a white dwarf, beginning its trillion-year cooling. The white dwarf that remains will retain something like a memory of our Sun's history, its rotation, the isotopic signatures of its composition, perhaps slight asymmetries from the gravitational influence of Jupiter and Saturn across 5 billion years of orbital dynamics. In some physical sense, the history of this solar system will be encoded in that cooling remnant for as long as the universe continues. No humans will be present to observe this. The realistic window for complex life on Earth is roughly 1 to 2 billion years, set not by the red giant phase 5 billion years hence, but by the gradual brightening happening right now. Either humanity will have found a way to move, to adapt beyond recognition, or the story of Homo sapiens will have concluded long before the Sun begins to swell. The Sun's death will happen in a solar system that has been uninhabited for billions of years. But, and this matters, the atoms will persist. The oxygen you just inhaled will still exist in 10 trillion years. Transformed, dispersed, scattered through interstellar space, perhaps eventually incorporated into a new molecular cloud, a new star, a new planetary system circling a star that won't form for another billion years. The carbon in your body, the iron in your blood, the calcium in your bones, none of it will be lost. The universe doesn't destroy matter, it redistributes it. You are not a permanent arrangement. You are a temporary configuration of material that has existed since the first supernovae, material that will exist long after the last trace of what we'd recognize as civilization has dispersed. I want to be honest with you about something. I started building this video planning to center it on the dramatic deaths, the supernovae, the black holes. Those are easier to make vivid. The collapse in 0.1 seconds, the shockwave, the blinding flash. But the more I spent time with our Sun's actual fate, the more I found it doing something different to me than excitement. Clarifying, maybe. The universe doesn't owe us spectacle. It gave us 10 billion years of warmth and light and the specific chemical conditions for a biosphere capable of asking questions about its own origins. And when the fuel runs out, it will quietly transform everything we ever were into the raw material for whatever comes next. That's not a consolation prize. That's the actual deal. And sitting with that feels like enough, more than enough. At the beginning of this video, I said somewhere in this galaxy, a star is taking its last breath right now. That's statistically true, roughly 1 to 2 stars go supernova in the Milky Way every century. Which means within our lifetimes, there is a real, non-trivial chance that on a clear night, you will see a new light appear in the sky that wasn't there before. A star that had been burning since before Earth formed will announce its death with a flash visible across thousands of light years. And now you'll know exactly what you're seeing, not just a supernova, but the specific sequence, the iron core, the 0.1 second collapse, the stalled shockwave rescued by neutrinos, the shock breakout flash, the weeks of outshining an entire galaxy, and the neutron star or black hole left behind in the silence. Go outside tonight and find Betelgeuse. It's the red-orange star on Orion's right shoulder. Look at it for a moment. It's a red supergiant, roughly 500 light-years away, in the final evolutionary chapter of its life. When it goes, in a century or 100,000 years, we genuinely don't know. It will be the most spectacular thing humans have ever witnessed in the night sky without a telescope. And you, right now, are alive in the only brief window when you can look up at it while it's still there. In this space documentary, we traveled from the moment silicon begins to burn in a massive star's core, through the collapse that lasts a tenth of a second, the shockwave that almost fails, the explosion that outshines a galaxy, the quiet dissolution of a smaller star, the trillion-year cooling of a white dwarf, and the absolute silence of a black hole, all the way to the personal, unhurried farewell of a star like our own sun. What I hope you're carrying away isn't just a sequence of events. It's a shift in how you hold the word death when it applies to something this large, this old, this generative. Stellar death is not the end of the story. It is how the story continues. We are the continuation of a story that began in a star that died before this planet existed, and when our sun finally exhales its last breath, that story will continue in something we cannot yet imagine. If any of this changed how you see a sunrise, even slightly, the most meaningful thing you can do is share it with one person in your life who you think would feel the same thing. Not for the algorithm. Because this kind of perspective is genuinely rare, and the people around you who would appreciate it deserve to know it exists. And the next video we're making goes somewhere even darker and even stranger, into the time after the last star dies, into the era of no light, no warmth, just cold remnants and slowly evaporating black holes in an unimaginably distant future. Cosmologists call it the black hole era. It is the strangest, most disorienting thing I have ever researched. And somewhere in the darkness of it, there is something that I think you'll find unexpectedly beautiful. Until then, look up. The outro has already been written in the passage above. The video ends with, "Until then, look up," which is the complete, creative CTA that callbacks to the content, specifically the instruction to find Betelgeuse in the night sky and the broader theme of looking outward at the universe. The teaser for the next video about the black hole era serves as the final forward momentum before that closing line lands. The script is complete at the natural ending point established by the existing text. There is a detail I haven't mentioned yet, and I think it deserves its own moment before we close. Every element heavier than iron that exists anywhere in the observable universe, every atom of gold, every atom of uranium, every atom of platinum, was forged in the violence of a neutron star collision or a supernova. Iron is the endpoint of stellar fusion. The universe cannot squeeze energy out of fusing iron the way it can from lighter elements. So when a massive star dies and its outer layers get blasted into space, what gets released is everything the star managed to build over millions of years: carbon, oxygen, neon, magnesium, silicon, the whole periodic table up through iron, scattered across interstellar space at a fraction of the speed of light. The heavier elements, the ones beyond iron, are synthesized in the explosion itself and in the collision events that follow when neutron stars merge. That gold ring on someone's finger. The uranium fuel rods in nuclear reactors. The iridium layer in the geological record that marks the asteroid impact 66 million years ago. All of it, traceable back to stellar violence on a scale that makes a hydrogen bomb look like a match being struck. What I find myself returning to, and I genuinely didn't expect this when I started researching, is the sheer patience of the process. We talk about stellar death as an event, but for a star like our Sun, the transformation from comfortable middle-aged star to red giant is a change that unfolds across hundreds of millions of years. The Sun is brightening right now, gradually, at a rate that is completely imperceptible on human timescales. Over the next billion years, that brightening will push Earth's surface temperatures beyond the threshold where liquid water can persist. The oceans will not vanish in a catastrophe, they will evaporate slowly, over geological time, in a process so gradual that if you compressed it into a human lifetime, you wouldn't notice the change from one decade to the next. The end of Earth as a habitable world will feel, from inside it, like nothing at all. That's how complete the scale mismatch is between cosmic time and human time. And yet here we are, in the narrow corridor of conditions where it all works, the Sun bright enough to warm the surface, not so bright that it boils the oceans, the magnetic field deflecting the worst of the solar wind, the Moon stabilizing the axial tilt, the giant planets sweeping up debris that would otherwise crater the inner solar system back into sterility. The list of factors that had to land right is long enough that you can spend years studying it and still feel like you haven't reached the bottom. We are not at the center of the universe, we established that centuries ago. But we are, unambiguously, at an extraordinary intersection of conditions. And the Sun, dying star that it eventually will become, is the reason any of it was possible at all. There is one more thing about black holes that I want to leave you with, because the documentary version of a black hole, the dramatic, light-bending, time-dilating monster, sometimes obscures something even stranger about what they actually are over cosmological time. A black hole is not permanent. This surprised me more than almost anything else I encountered in this research. Stephen Hawking's theoretical work in the 1970s demonstrated that black holes slowly lose mass through a quantum process that produces what's now called Hawking radiation, extremely faint thermal radiation that leaks from just outside the event horizon as a consequence of quantum fluctuations in the vacuum of space. For a stellar mass black hole, the timescale for complete evaporation via Hawking radiation is so staggeringly long that it's essentially incomprehensible, on the order of 10 to the power of 67 years for a solar mass black hole, and longer still for the supermassive black holes at galactic centers. To put that in perspective, the current age of the universe is roughly 14 billion years, or about 10 to the power of 10 years. The evaporation timescale for a stellar mass black hole is 10 to the 57th power times longer than the current age of the universe. That is not a number that maps onto anything intuitive. That is a span of time so immense that the universe will have undergone changes we cannot even fully categorize before a single stellar mass black hole completes its evaporation. But the endpoint is real. Eventually, in a universe that has been dark for so long that the concept of dark will have lost most of its meaning, because there will be nothing left to contrast it with, the last black holes will finish evaporating. What remains after that is a subject that physicists approach with genuine uncertainty. A sparse scattering of photons, neutrinos, and whatever stable elementary particles are left. A universe at maximum entropy. A universe in which no further free energy is available to do any kind of work. The stars, when you trace this all the way to its conclusion, were not a permanent feature of the universe. They were a phase. A particular era, lasting from roughly 100 million years after the Big Bang until roughly 10 to the 14th years from now, what cosmologists call the stelliferous era, the age of stars. We happen to live near the middle of it, which is part of why the night sky looks so richly populated. Future civilizations, if any exist, living near the far end of that era will look up at a sky growing progressively emptier as fewer and fewer new stars form and the existing ones exhaust themselves. The darkness of the night sky will not be a mystery to them. It will be the observable fact of a universe winding down. But we are not at the end. We are in the middle of the most illuminated, most generative era the universe will ever produce. Right now, across 2 trillion galaxies, stars are being born, burning, dying, seeding space with the elements that make chemistry possible, that make biology possible, that make the question of what we are doing here not just conceivable but worth asking. Every star that dies contributes to the next generation of stars. The metallicity of the galaxy, the fraction of its mass in elements heavier than hydrogen and helium, has been rising for 13 billion years, enriched by every supernova, every asymptotic giant branch star that puffed its outer layers into a planetary nebula, every neutron star merger that scattered gold and platinum through the interstellar medium. The stars of this era are richer in heavy elements than the first stars, which means the planets that form around them are chemically richer too, which means the conditions for complex chemistry, for organic molecules, for life, are more prevalent now than they have ever been in cosmic history. We did not arrive too late. By some measures, we arrived at exactly the right time. The death of each individual star is, simultaneously, an investment in the continuation of complexity. That's not a metaphor. It's the literal mechanism by which the universe maintains its capacity for interesting things to happen. When you see a star as something alive, something burning through its fuel, struggling to maintain equilibrium against gravity's relentless pressure, eventually losing that fight and releasing its contents back into the galaxy, the word death starts to feel inadequate. It implies a terminus. What actually happens is more like a return. The material that built that star was borrowed from the interstellar medium. When the star dies, it pays it back, with interest, enriched, processed, transformed into something more complex than it was before. If you're someone who finds comfort in permanence, in things lasting, the universe probably looks like a disappointing place when you examine it closely enough. Nothing lasts. The sun will not last. The Milky Way will merge with Andromeda in about 4 billion years. The local group of galaxies will eventually coalesce into a single massive elliptical galaxy as the universe's expansion carries all other galaxy clusters beyond our observational horizon. Even protons, if current theoretical predictions are correct, have a half-life, though one so astronomically long that it makes stellar evolution look instantaneous. At the deepest level of physical law we can currently reach, nothing persists indefinitely. But if you can make peace with impermanence, and I think sitting with what we've covered today is actually useful practice for that, what you find is something different than loss. You find a universe that is extraordinarily good at transformation. The hydrogen that formed in the first 3 minutes after the Big Bang is still here, in different forms, in different configurations, doing different things than it did 13 billion years ago. The universe did not lose that hydrogen. It became us, and stars, and galaxies, and the thin atmosphere of a pale blue planet where something improbable enough to ask questions about all of this managed to assemble itself from the debris of ancient supernovae and develop enough complexity to be genuinely curious about where it came from. That is not nothing. That is, if anything, the opposite of nothing. The last 24 hours of a star are not really an ending. They are the most dramatic single moment in a story of continuous transformation that began at the dawn of time and will not resolve until the final black hole evaporates into a scattering of low-energy photons in a dark, cold, maximally entropic universe unimaginably far in the future. We are, right now, inside that story. The sun above you is mid-chapter. Betelgeuse is in its final pages. Somewhere in the Milky Way, a star we cannot currently see is on its last paragraph, and when it goes, the light from that moment will travel for centuries before it reaches us, appearing on some future night as a new star where no star was before, announcing a death that happened long before the message arrived. The universe communicates on timescales we have no natural intuition for. The fact that we developed physics, mathematics, and observational astronomy well enough to decode those messages at all, to look at a point of light and reconstruct the interior dynamics of a dying star hundreds of light years away, is one of the more remarkable things I know about this particular arrangement of atoms we call humanity. So here is the creative CTA that this journey deserves. The next time someone tells you they find space depressing because everything eventually dies, send them here, because they've misread the plot entirely. The stars, it turns out, are not a warning about impermanence. They are the most extravagant demonstration the universe has ever staged of what impermanence can accomplish, and if the last hour we spent together inside the physics of stellar death has done anything useful, I hope it's that. I hope it's shifted something in how the night sky looks to you, even slightly. Not smaller. Larger. Not quieter. More articulate. We started this journey dropped into the middle of a crisis, silicon burning in a stellar core, the last few hours before gravity wins a fight it has been losing for millions of years. We watched the iron accumulate, inert and catastrophic, a core that cannot buy more time by burning its own ash. We watched the collapse happen in a fifth of a second. We stood, in whatever imaginative sense is available to us, at the edge of a shockwave stalling inside a dying star and then being resurrected by a flood of neutrinos so powerful that even the feeble fraction that matter interacts with was enough to tear a sun apart. We watched that explosion outshine a galaxy. We followed the quieter story too, the sun's path, the red giant swelling, the planetary nebula blooming in slow motion across light years, the white dwarf cooling for longer than the current age of the universe. And then Betelgeuse. That particular story deserves one last moment, because it captures something important about how this subject lives in the space between science and human experience. For a few months in 2019 and into 2020, Betelgeuse dimmed visibly enough that amateur astronomers noticed without instruments. The internet, reasonably, lost its composure. Headlines ran. People went outside and looked up, which is actually a wonderful outcome regardless of the cause. And the cause turned out to be a dust cloud, a mass ejection that temporarily obscured the star's light as seen from Earth. Not a supernova. Not the end. The star was misbehaving, as red supergiants routinely do, shedding mass in asymmetric bursts, its surface convecting in cells larger than the entire orbit of Earth. It was theatrical. It was not dying that week. But here is the thing that I find genuinely worth sitting with: it will. Not on any timescale that is personally urgent for anyone alive today, and probably not for another 100,000 years at minimum, though the uncertainty range on that estimate is large enough to swallow civilizations. But within the lifetime of the galaxy as a populated, star-forming system, Betelgeuse will collapse. The shock wave will form. The neutrinos will arrive here, at Earth, about 8 minutes before the light, because they travel at nearly the speed of light and pass through the planet as if it isn't there, while the light has to navigate around interstellar dust. Neutrino detectors buried deep underground, originally built to study things like solar neutrinos and reactor physics, will register a burst of thousands of counts in seconds and alert astronomers before anyone can look up and see anything. Then the light will arrive. And for a few weeks, there will be a star in the sky visible in daylight, casting faint shadows at night, appearing near the shoulder of Orion, right shoulder, since Betelgeuse marks that position, and every human being alive at that moment who knows to look will see, with their own unaided eyes, a star in the process of becoming something else. That is not a tragedy. That is an event. That is the universe being legible to the creatures it accidentally produced. We covered the black hole formation pathway, the most extreme outcome available to the most massive stars, and I want to leave one image from that section with you, because I think it is the strangest and most structurally interesting thing in all of stellar physics. When a black hole forms from a stellar collapse, the matter that crosses the event horizon does not, from the perspective of a distant observer, actually cross it in any finite amount of time. Due to gravitational time dilation, the way intense gravity stretches time itself, an observer watching from outside would see infalling matter slow, redshift, and asymptotically approach the event horizon, appearing to freeze there, growing dimmer and dimmer as the photons take longer and longer to climb out of the deepening gravitational well. The matter appears to stop. It never quite disappears. The event horizon forms, in this observational sense, as a limit that matter approaches but does not reach within observable time. The black hole, as seen from the outside, is a kind of cosmic record of everything that ever fell into it, not gone, exactly, but frozen at the threshold, a permanent archive of its own feeding history written in redshifted light that grows too faint to detect almost immediately. Meanwhile, from the perspective of the infalling matter itself, if any perspective could survive long enough to be meaningful, the crossing happens in finite time, and what waits on the other side is a region where our current physics simply ceases to generate reliable predictions. The singularity, that word borrowed from mathematics to describe a point where equations produce infinities and therefore stop being useful, may not be a real physical object at all. It may be a marker where general relativity breaks down and quantum gravity, a theory we do not yet fully have, takes over. What actually happens at the center of a black hole is one of the most consequential open questions in all of theoretical physics. We know what the outside looks like. We have no agreed-upon account of the inside. The universe keeps at least one room locked. The outro to all of this, and I am aware that calling it an outro makes it sound more formal than I mean, is not a summary. You have been here for nearly an hour. You do not need a summary. What I want to leave you with instead is a posture. A way of carrying this. The atoms in your left hand were forged in a star that died before our solar system existed. Calcium, iron, carbon, oxygen, none of them were produced in the Big Bang. All of them required stellar interiors and stellar death to exist. When you hear that for the first time, it often feels like a piece of trivia, something to mention at a dinner party. The more you sit with what we covered today, the actual physics of how those elements got forged, the actual violence of the process by which they were dispersed into space, the actual timescale over which they drifted through the interstellar medium before finding their way into a molecular cloud that collapsed into a new solar system, into a rocky planet, into the ocean, into chemistry, into you, the less it feels like trivia and the more it feels like biography. Personal history, just written on an incomprehensibly longer timescale than we usually allow ourselves to read. You are, in the most literal physical sense available to us, a product of stellar death. Not metaphorically. Elementally. The iron in your blood completed its last nuclear fusion reaction inside a massive star that then exploded, probably somewhere between 4 and 7 billion years ago, in a region of the Milky Way that no longer looks anything like it did then. The shockwave from that explosion, or more likely the shockwaves from several such explosions in sequence, may have been the trigger that compressed the molecular cloud that eventually became our solar system. The deaths of those stars may have caused the birth of ours. Your existence may be downstream, in the most direct causal sense, of a supernova. Probably more than one. I didn't invent that connection. The physics did. I just wanted to make sure you felt it, not just understood it. And because we have been together through a genuinely large amount of cosmic catastrophe today, here is one more thing before we go, the part of this subject that I find most quietly remarkable, and that doesn't usually make it into the lecture version of this material. The universe has no particular stake in being understood. It does not generate legible signals for our benefit. It does not produce phenomena on timescales convenient for human observation. A stellar collapse happens in a fraction of a second. A star's main sequence lifetime runs to billions of years. A white dwarf cools to invisibility over timescales longer than the current age of the universe. None of this was calibrated for us. And yet here we are, having decoded enough of the underlying physics to reconstruct the interior of a dying star with enough confidence to say, with genuine predictive power, what will happen inside Betelgeuse when it goes, before it happens. We worked it out from first principles, from the behavior of particles in laboratories, from equations that were developed to describe other phenomena entirely, and we assembled a picture of stellar death that we can test against real supernovae when they occur and have repeatedly found to be, in its broad structure, correct. That is a specific kind of miracle. The secular kind, the one that doesn't require anything supernatural, just the improbable convergence of curiosity, mathematics, observation, and enough time for one species on one planet to get sufficiently organized to do the work. We are, as far as we know, the only part of the universe that has ever looked at itself this carefully. The next time you're outside on a clear night and you can see the stars, not the concept of stars, but the actual points of light, the ones that are genuinely there, the ones that are mid-process, burning through fuel they borrowed from the Big Bang, losing a fight with gravity that will end in fire or collapse or the long slow cooling of a white dwarf. Remember what you now know about what those lights actually are. Because knowing changes the looking, and you have come too far today to ever see a star the same way again.